Welcome back, chemistry fans. Tonight we are going to do your homework for Unit 13, Topic 2. It's a little bit tricky as we go through it, so stay with me. It starts off very, very easy, and then it starts to get a little challenging. So here we go. We're going to start first with number 1, very simple task. Defining Bronsted-Lowry base, what you need to know is that there are 2 different ways in which we define acids and bases. The Arrhenius method dealt with acids being identified by H and bases being identified with OH. Now, the Bronsted-Lowry, though, fixed some of the little issues that were out there. The acids still are identified by H, but what they say now is that it donates an H, whereas the base will now accept the hydrogen ion. Okay, the name. So this is a polyatomic ion. We need to recognize that SO4 is sulfate, and what that means is that it has the suffix -ic on it. And so what we then are going to do is make this into an acid. There will be no prefix on it because it is polyatomic. So it just becomes sulfuric acid. All right, number 3, simple task as far as pH is concerned. pH is equal to negative log of the hydrogen ion concentration. Well, they don't necessarily give you the hydrogen ion concentration. What they give you is the concentration of HCl. We have to dissociate this and understand that it's going to break apart into 1 piece each. This concentration of the HCl is going to separate, and it will be in equal concentrations. It's not going to split half and half. It's going to split for every 1 of 2.9 times 10 to the negative 9. It will create 1 that is 2.9 times 10 to the negative 9. So they stay, both of them will have the same concentration because they're going to split 1 for 1 on this one. So our hydrogen ion concentration ends up being what is provided to us. So we will just simply do negative log of 2.9 times 10 to the negative 9, and we get something like 8 point, I can't remember, negative log of 2.9 to the negative 9, and that is 8.5 as the pH. It is unitless. Okay, now we get into the hard stuff. And what we have to understand about number 4 is this idea that again, H3PO4 is going to dissociate. However, it is going to dissociate 1 at a time. It's going to dissociate into 1 hydrogen ion, and whatever is left over will be there. So we would have to calculate the Ka value, or we'd have to be given the Ka value of each of the 3 to find out what happens as it loses all 3 of its hydrogens. It's only going to lose them 1 at a time. So we have an initial concentration of 6.2. We don't know what these concentrations are. So they end up actually just being X values, just like they were before. Now, what this Ka value does for us is it allows us to set up a ratio of how it dissociates, products over reactants. And so it is this ratio of 3.9 times 10 to the negative 6 is equal to the products, which we don't know, but we could just now combine them together as X squared over the initial concentration of 6.2. So now I'm just going to simplify and solve for that X. So I've got 3.9 times 10 to the negative 6 multiplied by 6.2, and what I get is X squared is equal to 2.42 times 10 to the negative 5. So we're going to do the square root of that to solve for one of the X's. My X value would be 0.005. All right, now we're going to plug that back into pH is equal to negative log of the hydrogen ion concentration. In this case, it's X. We got negative log of that, negative log of that value, and I end up being, and you end up being 2.3 as your pH. Okay, this is everything that I wish to share with you tonight. So again, gets a little bit tricky and a little bit complicated. Hopefully it's getting easier with some of the practice examples that we do in class. Thank you so much. Talk to you again soon. Bye-bye.